Hello everyone, welcome to day 3. Yesterday I completed till STL Java collection section. Today we'll start with this basic mathematic questions. So coming to the first question, count all the digits of a number. We'll see the example. So given an integer n, we need to return the number of digits in n. Okay. So there are multiple ways to do this question. I think I've done this question before. So one of the easiest ways of doing this would be if we convert this number to string, and then we can simply use the inbuilt string.length method to find the length of the number of digits in this. But I think that is not appropriate solution for interviews, but that is one of the ways. So if you see, one way is to convert to string. We'll take the number n, then we'll convert it to string. For that we can do integer dot to string, I guess, or string dot value of and integer dot to string also works. We can use either of them, and then we can print the value. So this is one way of doing this. So if the number is this, the result will be 6. Okay. Now the other way of doing this would be, what we can do is, the brute force solution for this would be that we take a while loop, and in each iteration we'll divide this number by 10 until this number becomes 0, and the number of iterations will be the number of digits in this. So write the brute force approach. We can take a while loop. I'll take one more integer m equals to n so that we don't lose the value. So while m is greater than 0, what we'll do is, we'll take a counter which will be 0 initially, and we'll do count plus plus, and in each iteration we'll do m equals to m by 10. So we'll divide it by 10 in each iteration, and then we'll print the result. Count is the result. Okay, so let's try it out. So both of them gives the same result. So the Time complexity for first one is order of 1, and for the second one I'm not sure if this is order of 1 and how it works internally. So we cannot for sure say it's order of 1 because it depends upon the internal implementation of this two-string method. This time complexity for second one is so in each iteration the number is getting reduced and it is getting divided by 10. That means the time complexity will be log 10 log base 10 of n. So one simple way I'll tell to find the time complexity of similar kind of approaches is that whenever whenever the input is getting or the this n, the input size is getting reduced in each iteration, and let's say in binary search we divide the input in divide by 2 in each iteration, right? So the search space reduces by half in each iteration. That is why the time complexity of binary search is log 2n. Log 2 is basically log base 2 n, because we are dividing the whole search space by 2 in each iteration. Similarly, if in any question if the search space is getting divided by 3 in each iteration, so the time complexity will be log 3n and so on. So in this question the search space, or you can say the input, is getting divided by 10 in each iteration. That is why the time complexity will be this, plus some constants because we are doing other operations also. So we can say this plus some constant value which can be ignored. So this is other way of doing this. There is one more way of doing this question is the most optimal solution. So as we realize that in each iteration the search space or the input is getting divided by 10, so we are doing log 10 n operations to make this number as 0. So what it represents is that this can be represented as the number of digits in this number. How? Because that is what we are doing in each iteration. When we are dividing it by 10, we are subtracting one digit from the, not subtracting but removing one digit from the end of this number, and to make it 0 we are doing it these many times. That means this is the number of iterations and this is the number of digits plus some constant to make this number 0. So the optimal solution would be if we can somehow calculate the number of digits in this number by just using this formula. So let's say if the number is n, we can understand by taking an example. So let's say if the number is 10, okay, then log 10 of 10 is 1. So as a result we know that there are 2 digits in 10, so we'll say that answer would be log 10 of 10 plus 1, okay, which will be 2. So there are 2 digits in 10. Similarly, if it is 100, then log 10 of 100 is 2. It's 2. That means the answer would be log 10 of 100 plus 1, that is 3. So there are 3 digits in 100. What if we take a number in between these? So let's say the number is 57. So log 10 of 57 is 1 point something. Okay, that means if we take it as an integer, then log 10 of 57 plus 1 will give the number of digits, that is 2, right? So what we can say from this is from 10 to 99, the log 10 value of 10 to 99 is 1. That means to find out the number of digits in any integer, what we can do is we can calculate log 10 of that number plus 1. That would give us the solution. So we can write it as result equals to math dot log 10. I think that is the function. I'm not sure, we can check later if it works or not. Log 10 of n plus 1, this will be the number of digits in n. We'll do system dot out dot println result. So let's see if it works. Okay, we will convert it into int and then add this number. So the result is 7 even in this case. Now coming to the time complexity. So this, we are calculating the number of digits in this case in order of 1 or constant time, because there is only one operation. So I think these are the 3 solutions for this. If you are not able to come up with this optimal solution without looking at any help or any help section on the question, it is completely fine. I was able to come up with this in one go because I had already, as I said, I had already done this question before, so I knew something like this is possible. But if you're not able to, that is also completely fine. So now that you have seen, we can come up with such solution if whenever even in similar kind of questions, whenever the search space is getting reduced by n, so the number of iterations are generally like this, where this number or the base is the number by which we are dividing it. Okay, I'll quickly go through the solutions they have given. So initialize this number, n is greater than 0, increment by 1, update n by dividing last digit, removing the perform a modulo operation in it, update n by removing its last digit by performing a modulo. Wait, how are they going to remove the last digit by performing modulo? They should divide. This is not correct, I think, but okay, we know what they mean, but I think this is not correct. And the optimal solution is same thing, log base 10 n plus 1. Now we'll go to next question. We'll mark it as complete. So given a number, we need to reverse the number. Okay, so again, the easiest way of doing this would be just to convert it to a string and then reverse the string. The other way of doing this would be similar to this one. So we'll take out the last digit. So what we are going to do is, in each iteration we'll create a while loop, and in each iteration we'll extract the last digit by taking a modulo by 10 of this number. We'll take out the last digit and add it to a number which we can call as a result, which will be initialized to 0. We'll add this number to that result and then multiply it by 10, and then divide this whole initial number by 10. So I'll show this. We'll keep everything as same, and we'll also, instead of count, we need a result which will be initially 0. In each iteration we'll make result equals to result into 10, and we'll add a number plus equals to m modulo 10. We'll add the last digit and then we'll divide m by 10, and result is the solution. I'll run this code. Okay, so the reverse number is 8765, and again the time complexity of this would be again log 10n, because in each iteration we are dividing this number by 10 until it becomes 0, plus some constants which we will not write. I will also dry run this code. So let's say if let's take this example 5. For simplicity we'll take the initial number as 567. So in first iteration result will be 0 into 10, which is 0, and result equals to result plus m modulo 10. M modulo 10 is 7, which is the last digit, and we'll add this to result. So result will become 7 and m equals to m by 10. So we're dividing this number by 10, so m will become 56. Okay, in next iteration result is now 7, then we are doing result equals to result into 10, so result is 70, and then we are doing m modulo 10 and adding it to result. So m modulo 10 is 6, and we are adding it to result, so result is 76, and then dividing m by 10, so m is 5. Now again in next iteration result is 76 into 10, which is 760, and then result is m modulo 10 is 5, and we are adding it to result, so it is 765, and then m equals to m by 10, so m is 0. And now when m is 0 we'll break out of this loop and print result. So now our result is 765, which is the answer. So that's all. I'll quickly go through the approach. Loop through the original, extract the last digit, multiply by 10, remove the last digit by dividing by 10, continue this process until it becomes 0. Fine. Mark it as done. Palindrome number. Okay. Given a number n, return true if it's a palindrome, else return false. Okay. So I think one way of doing this is again converting it to string. I will not do that. The other optimal approach of doing this is reverse this number and store it in some other integer variable and then compare both. So as we have already written the reversed logic, what I'll do is at the end I'll just compare if result is equal to n, that means it's a palindrome. Else it is not a palindrome. Palindrome की spelling यही होती है, palindrome. Okay, so I'll run this code. Okay. This is a palindrome. I'll run for one more example. 1 2 3 4 5 2 1, not palindrome. Okay, we'll go through the approach. So initialize reverse number as 0. Then what we are doing is make a duplicate of original number and store it. Okay, they're showing the same thing, and if they are equal, return the number as palindrome, otherwise not. Fine. So this is also done. We'll move to next question. GCD of two numbers. So we are given two numbers, n1 and n2, and we need to find the greatest common divisor of both the numbers. Okay. Okay, so the greatest common divisor of both the numbers is the greatest number which can divide both of these, right? So that number would be less than this and less than this, less than both the numbers, right? So we can run a loop from 1 to this number, 1 to the maximum of these two, and then we'll see if we'll keep it iterating till n2, and we'll find the maximum number which can divide both. Or wait, instead of doing it till n2, because any number which is greater than 9 cannot be a divisor of 9, right? So instead of looping till n2, we need to loop till minimum of these two, right? That will give us the result. So we'll loop from 1 to minimum of these two, and we'll find the greatest divisor. So I'll write the code. First of all, we need to take two inputs here instead of 1. Enter the first number. Enter the second number, and we'll take it in n2. Now we'll take an integer min equals to math dot min of n1 and n2. Okay, and then we'll run a loop from int I equals to 1, I is less than equals to min I plus plus, and then we'll take a result as 1, or we'll take a GCD as 1. Okay, so initially the greatest common divisor is 1. Now if n1 modulo I is 0 and n2 modulo I is also 0, that means GCD is now n1. GCD is now I. So as we keep iterating, we'll keep finding the next greater divisor, and at the end we'll find the greatest divisor of these two, and then GCD will be the result. Let's see. First number is 9, second number is 12, GCD is 3. Okay, 20 and 15, GCD is 5. I'll try one more example. One second. I got a pager alert. One second. Hmm. 20, second number is 15, so GCD is 5. Perfect. So that is one way of doing this. Okay, so what we are doing is we are looping from 1 to minimum of the numbers, and we are looping till we find a divisor of both. What if we start looping from minimum and till 1? So we start from the biggest number and then loop till 1 and do I minus minus. So the first time, in that way, what will happen is the first time we find the divisor of both, that will be the greatest divisor. Then we don't need to loop further. I think that will be the more optimal solution for this. Why? Because in this way, what we are doing is, even if we find a divisor, we still need to loop ahead and see if we have a more greater number which will divide both. But if we loop backwards, then we'll have to loop only till we find the first divisor. Time complexity will remain same, which is order of so time complexity of this will be order of minimum of these two, n1 and n2, whichever is minimum till that number we are iterating, so that will be minimum of these two. Even in the other approach which I am saying is we start from min till 1, even in that one the time complexity will be this, because let's say for worst case, if the GCD is 1, then we'll have to anyhow iterate till 1. So worst case scenario will have the same time complexity, but I think it will improve the average case. So the other approach would be, we'll start from min, iterate till I is greater than equals to 1 or I is greater than 0, and we'll do I minus minus. And if if we find such case, then we'll just do a break, and that will be the GCD. We don't need to iterate further. First number is 20, second number is 15, GCD is 5. Fine. Okay, we'll go. So they have given 3 approaches. Okay, let me go through these. So first is brute force approach, in which we initialize a variable GCD as 1, correct? This variable stores the greatest. Iterate from 1 to minimum. We start from 1 because GCD of any number is at least 1 and greatest. Okay, and in each iteration, if a common factor is there, then we update the GCD variable. So this is what I've done. This is what is the better approach. Better is if we iterate them from minimum down to 1. Okay, I think that is what they're talking about, the second thing I did. So we reduce the number of iteration because we start from potentially largest common factor, correct? Okay, so this is a better approach. Then what is the optimal solution? Okay, it's something called Euclidean, कैसे पढ़ते हैं इसको, Euclidean algorithm. Okay, This is a method for finding the GCD of two numbers. It operates on the principle that GCD of two numbers remains the same even if the smaller number is subtracted from the larger number. Okay. To find the GCD of n1 and n2, where n1 is greater than n2, repeatedly subtract the smaller number from the larger number until one of them becomes 0. Once one of them becomes 0, the other is the GCD of original number. Interesting. Okay. So n1, if n1 is 20, n2 is 15, then GCD of 20 and 15 will subtract these. It will become 5 and 15. Then we'll again subtract these. It will become 10 and 15. How come it will become 10 and 15? 5 minus... Okay, they have reversed these numbers. 5 will remain same and we are subtracting 5 from 15, so it is 10. Now again we'll subtract, so it will become 5, 5. Again subtracting will become 0, 5, and then 5 is the GCD. Okay. This is interesting. I wasn't aware of this. But why it works? Let me search about it more on Google. For two numbers remains the same when the largest number is replaced by the difference. That is what they are saying, that it remains the same, but why? The thing is, until I'm not able to visualize a algorithm or a function, a theory in my head, it becomes very difficult for me to accept it. So they are saying it is a principle, but why? Somebody has asked the right questions. I'm having trouble understanding why this algorithm of finding this two number always works. I still don't understand why. We subtract. Why? But why? Let's see on YouTube.
Welcome to this proof of concept video. Today, the goal is to describe the Euclidean algorithm with a visual approach, so it's intuitive enough that you can always figure it out and use it, even if you've forgotten it. Please don't ever use mnemonics and memorization when you're learning math. That may get you through a quiz, maybe, but it's useless beyond that. And if you rely on it regularly, you actually gradually accumulate a deficit in the creative thinking skills that you really need, and math gets harder and harder to keep up with. So instead, to really internalize mathematics, it's important to build it for yourself. The placing of the building blocks in your mind using your own muscles is what you learn from. So the point today is to guide you to build the Euclidean algorithm for yourself in a visually striking way so that you'll always be able to recreate it for yourself, no memorization involved. So we'll use visual intuition today, but check out our next video for a different fun and famous visualization of the algorithm in action once you're more familiar with it. We've already talked about the GCD, or greatest common divisor of two integers. It's the largest integer that's a factor or divisor of the two that you've got. So, for example, the GCD of 15 and 12 is the biggest integer dividing both of them, namely 3. If you'd like a primer on how to think about the GCD, check out our other videos via the links below. But in brief, I'll assume that we're used to thinking about the GCD in terms of the prime factorization of two integers. That's why I've shown the factorizations of 12 and 15 here, so that you can see the 3 sitting in there as the biggest and, in fact, the only thing they have in common. For one more example, the GCD of these two medium big integers is easy to determine because of...
By the way, you can skip this part if you don't want to go through all these explanations, but I would like to go through that.
Handed them to you in factored form. You just have to pick out the common factors and keep those. So I can go prime by prime. So here I can grab a single 2, 2 3s, 1 5, and 1 7. Somehow, in my head, these prime factors are building blocks, and if we put both of the castles that they form on top of one another, the GCD is the common part, it's the overlap. So taking a GCD of factored integers is easy. But as you may have heard, factoring integers is a challenge. We don't have any efficient methods to factor big integers. In fact, we've based much of the security of the internet on the assumption that no one in the world knows a clever, fast way to factor big integers. If someone did, they could upend the entire world overnight. So you might expect it to be difficult to take a GCD without factoring. But what we'll see today is that, surprisingly, there's a very fast algorithm to compute the GCD. It's called the Euclidean algorithm and dates back many thousands of years. I think of it as one of the first, most fundamental algorithms in mathematics. It's kind of striking that it's even possible, and yet it's actually very simple. We begin by imagining that you have two big numbers. Here they are, on screen, as two piles of stones. You want to take the GCD, but you don't even want to count all those stones, never mind factor the result. So now here's how we're going to do this. I'm going to compute the GCD of these two numbers like I'm playing some sort of children's game. Okay, I'm going to show you the rules and go through the process without telling you why it works, yet anyway, and you can see if you can catch the trick. So let's call these pile A and pile B. I'm going to manipulate and change them, but they'll always be pile A on the left and pile B on the right. First, I'm going to look for copies of pile A inside pile B. I can see 2 of them here. There's nothing special about the positioning of the stones. I'm just going to count out enough stones to call it a copy of pile A. And then I can see that I can actually do it twice without running out of stones. So there are 2 copies of A inside B. Then the rules of the game are that once I've found a copy of the smaller pile in the bigger one, I can subtract it off, by which I mean just remove the stones. So I subtract 1 copy of A and then another copy of A, and then what's left I'll call the new pile B. So now B is the smaller one, so I look for copies of B inside A. I think I can count off at least 1 copy of B, so I subtract it off and I'm left with a new pile A. Now A is smaller, so I look for copies of A inside B, and I see 2 of them. I subtract each of them off in turn, and that gives me a new pile B. Now notice how quickly the piles get small with this process. They're very small now, but I can do it one more time perhaps. Let me identify a copy of B inside A and subtract it off. Now I have 2 small piles. They're so small that I can see that they have 3 stones each without even bothering to count. Now here's the trick. I claim the GCD of the original 2 pile sizes is the same as the GCD of the diminished pair of pile sizes. So the GCD I'm looking for is the GCD of 3 and 3, which is pretty clearly 3. So does it really work? Here's the actual pile sizes. They were 21 and 54. Factoring these, I can see that, indeed, they have a GCD of 3. So it does seem to work, at least in this example. I claim it always works if you follow the process that I demonstrated. Okay, so why does it work? I'll show you the secret with a visual trick in a moment, but I encourage you to stop the video right now and ponder. Why does this work? Go ahead, pause and ponder. It'll stay with you so much longer if you figure it out for yourself. Okay, I hope you have a guess or an idea about why this might work, because once I show you with a visual what's going on, you'll never have this opportunity to figure it out for yourself again. Do you want to pause a little longer? Go ahead. Okay, fine. So you want to see my secret. So here it is. I'm going to silently step through the process again, but this time with a tiny little something added on top of the visual. Did it click? I drew little triangles over the stones to group them into threes. This represents the fact that the number is divisible by 3. So remember, the GCD was 3, meaning that this is possible. Both piles are made up of an integer number of groups of 3. So now, watch as I step through again how the process I described never breaks up a group of 3. If a pile is divisible by 3, you can subtract off some number of 3's. So what's left is still a multiple of 3. So watch it happen again. So this is an example of a cool, useful paradigm in mathematics. If you have a tough problem, replace it with an easier problem that has the same answer. So in our case, the trick is to replace the GCD of A and B, that's the tough problem, with the GCD of A and B minus A. That's the easier problem. Those are the smaller piles. So the answers are the same, but the new problem is simpler to deal with.
Got it.
So that's the Euclidean algorithm. Just keep simplifying the problem by subtracting one pile of stones from the other until the answer is just obvious. So I hope this explanation will stick with you and allow you to rediscover the Euclidean algorithm and make it a little faster. So GCD of A and B is the same as the GCD of A and
Got it. So this is because we are just simplifying it to smaller problem, because at the end, if you're saying that 5 is the common divisor of both of them, that means that even if we subtract both the numbers, the number we are subtracting, that will also be divisible by 5. So we can simply remove it, and at the end will come up with the result. Cool. It's interesting to see what will be the time complexity of this. So it will be minimum of n1 and n2. Okay, sure. I'm done for today. We'll see you tomorrow.